In the work that we've done on second-order linear constant coefficient differential equations, we've seen that sometimes we get solutions that oscillate, that go up and down, and it's due to trig functions being in the solution formula. Everything in this video is in bits and pieces being covered already, but I just wanted to put it all in one place. I just wanted to talk about some specific things we can do when we wind up with one of these kinds of solutions that oscillate. So what we're talking about are the undamped and the underdamped cases. These are the ones that result in oscillatory behavior. So undamped means we don't have a B term, right? So, but the C is positive. That's undamped. I should say that if we are talking about a mass on a spring, right, that C would be usually written as a K. Okay. Or maybe there is damping, there is a B, but it's underdamped, so that the B squared minus 4AC is negative. And again, in a mass on a spring, instead of A and C, we would have M and K. B is still B. So this would be B squared minus 4MK being negative, where M and K are positive. And if that's negative, that's called underdamped. Right. So the solutions are very similar. They both have the cosine and the sine terms. In undamped, it's just pure cosine and sine terms. In underdamped, there's also an exponential, right? But both of these functions oscillate. They go up and down. So pure oscillations just oscillate at the constant amplitude forever. If you have an exponential in there, then that exponential is going to sort of change the amplitude over time. If your alpha is a negative number, as it would be with a mass on a spring, the oscillations die out exponentially. But there would be differential equations where the alpha would come out positive, and then the amplitude would actually grow exponentially. All right, so this is what we're looking at. Now I want to focus on the cosine plus sine part of this, sort of this guy. Of course, in the underdamped case, we can always just factor out that e to the alpha t and just have that hanging out on the outside, and then what's in parentheses is exactly the same. Oh, I'm sorry, I forgot my b here. So yeah, what I want to do is just focus on expressions of this form and some information we can pull out of it. And as I say, this is information that we've already talked about here and there, but I just want to again go over it so it's not confusing and it's not lost in the mix. Okay, so let's just focus on these expressions whatever differential equation they may come from. A cosine something t, I'm using omega here as a generic variable, a cosine omega t plus b sine omega t. And let's just talk about this behavior. It is oscillatory, we've already said. It's basically an up and down periodic function. The period will be 2 pi divided by that number in there, that omega. And the frequency will be, the frequency is the reciprocal, it's that omega divided by 2 pi. Period and frequency are reciprocals of each other. Period, so if we look at the picture, the period is the amount of time it takes for one full cycle, right? So if you just pick 2 points that are sort of in the same, at the same point in the cycle, sort of like I've picked off 2 points that are crossing the x-axis going downward, there and there. There'd be another one over here. But these are 2 consecutive times when we're sort of at that stage in the cycle. And so from there to there, like the amount of time it takes to do a full cycle, that's a period. And so that's what that's giving us. It's capital T equals 2 pi over omega. The frequency is the number of cycles in one time unit, whether it's 1 second or 1 minute or whatever. It's how many cycles per second, say. So that would be that's the flip, that's the reciprocal of the period. Okay, so when our expression is written this way, we can get the t and the f. We can get the rate at which it's oscillating, either in terms of the period or the frequency, whichever one makes the most sense for us. Okay. However, there are two things that we can't get directly from this expression, and there are two things that we might want to also know. One is the amplitude. So the amplitude when you have oscillatory behavior is, right, this thing goes up to a certain maximum height and a certain minimum height, and it's centered at 0. So, if it goes up to plus a, let me not use a, plus k, it goes down to negative k, right? So that's called the amplitude. So again, it goes up to like sort of positive a number, and then it goes down to negative a number, and those numbers are that's the amplitude of the oscillation. The amplitude is not A or B, although it does come from A and B in a way that I will discuss in just a second. But yeah, we don't have the amplitude just written in front of us in this formula. We have to derive it, and I'm going to show you how. The other thing that this does not tell us is at the starting point, where are we starting in the cycle? That depends also on the A and the B, it turns out. You can see in this picture I've drawn, we're kind of starting it like right before we've reached the maximum, but not at the maximum. So like where the initial point of this function, where in the cycle is it starting? Okay, so neither of those things are obvious in this format. So it turns out there's another format that we can use, and we can convert this format into. So it turns out that this expression, sum of a cosine and a sine with different coefficients in front of them, can always be converted to or from a single cosine with a single coefficient with the same argument, omega t, only shifted by a certain amount, which I'm calling delta. So we can always convert from here to here and from here to here. The conversion formulas are the c, to go from this to this, c is the square root of a squared plus b squared, and the delta is the inverse tangent of b over a. So it's actually very similar to polar coordinates type conversion formulas, and actually that's where it kind of comes from if we delve into the actual proof of how you go from here to here, which I'm not going to do here. If you want to go back, if you have c and delta and you want to get back to a and b, a is c cosine delta and b is c sine delta. Again, that's like the polar coordinate. That's like going from polar back to rectangular. So these are the conversion formulas, and you can turn any expression like this into an expression like this. Now, when it's in this form, we can a little bit more easily read off some additional information. Now, first of all, let me just point out that we still have the omega, so we can still get the period and or the frequency from the omega using the same formulas. Okay, but now, because it's just a simple and single cosine, right? Cosine by itself would on its own go up to 1 and negative 1. And we're multiplying this by c. So this function will go up to c and down to negative c. So the c is the amplitude. So this allows us to get the amplitude. Right? Now, of course, c, remember, was square root of a squared plus b squared. So really, if we have a and b, we can get the amplitude, but we have to do this conversion. Okay. Now, the delta, what does the delta tell us? Well, the delta is going to be tied into the starting point of the cycles, as I was mentioning earlier. Let me try to explain this. If I just rewrite that one more time, where I'm going to, within the cosine, I'm going to factor out the omega from the t, and then I'm just going to force a factoring out of an omega from the delta, like that, right? Okay, so now I can see that what's going on here is, if you remember some sort of pre-calculus type material, t minus delta over omega, that means we're shifting the basic shape over to the right by delta over omega. So you may remember that. You may remember that you can shift, horizontal shifts of functions are achieved by subtracting or adding from the t or x or whatever the independent variable is. And when you're subtracting, that's a shift to the right. So we are shifting to the right by delta over omega. So before the shift, we would have sort of a standard cosine, and we know standard cosines start up at their peak. Right? We're going to just shift this over to the right, so it's going to be over here. And I didn't mean that to go through the origin. It doesn't necessarily go through the origin. It just shifted by some amount, so that from here to here is delta over omega. So in effect, since it's telling us how the basic cosine is shifting over, it kind of is telling us now what part of the cosine curve is hitting the the y-axis. Okay, so that information is right there. As a quick example, suppose we, after solving a differential equation, end up with a function that looks like this. Now, right off the bat, we know this is, oscillatory behavior. I'm not including an exponential here, so if it literally is this, then it would be not decaying down to zero or growing exponentially. It would just be consistent up and down oscillatory motion. We can immediately see what the period and the frequency would be. The period would be 2 pi over 4, so pi over 2. And the frequency would be the reciprocal, so 2 over pi. All right, so that much we can tell, but if we want to know more, especially the amplitude, that's the big thing. If we want to know the amplitude of these oscillations, we would need to convert, or at least do the a squared plus b squared thing. Yeah, so c is the square root of 4 squared plus 7 squared, giving us the square root of 57. And the delta would be the inverse tangent of b over a, so negative 7/4, which is negative 1.052, rounded. Okay, so the alternate form would be square root of 57 cosine of 4t, and then it would be minus delta, so actually plus 1.052. Okay. So now we know the amplitude is the square root of 57. And we can draw a quick sketch on our own without the need to graph on a calculator. So by the way, just to make this a little bit easier, since I changed my delta to decimal, let me also convert my t to decimal as well. That would be 1.571. Okay. Just rewrite that here. T equals 1.571. All right, so based on the phase shift, I know that, so delta was actually negative, so this is plus 1.052. So this actually got shifted to the left by 1.052. So 1.052, remember that's sort of where we start the normal, the standard cosine, which starts at the top of its peak. So we're up there. And then we know that this is going to do one full cycle in 1.571. So of course that's going to bring us past 0 to somewhere around maybe there. Yeah, something like that. So this is going to do one full cycle. It's going to go down and then back up again, which is one full cycle in that amount of time. So it's going to kind of do that. So that's got the correct period, and it's starting at the right place. And then, of course, it's just repeat. Like that. Okay, so that's the idea. So the relevant information to sort of at least picture in your mind, if not to actually draw a graph on your own, a rough sketch, is available in the numbers that we're looking at right here. Okay.